Okay. So, were you able to see the video Friday?
Yeah.
Okay, good. So in the lecture Friday, we were going over composition of functions. So what that meant was that if we have two functions, say f of x equals x plus 2, and g of x equals x squared, that we can actually take one of these functions and plug them in for the x in the other function and get an entirely new function, something that we would call f composed of g or g composed of f. So let's go ahead and try that out again. So let's say that I do f composed of g of x. Well, what that means is that I'm using f as a framework. The first one that comes in this composition is the framework. So I'm going to do x plus 2, but instead of writing x, I'm going to open up parentheses to plug something in there. So we should start out with something that looks like this. Then I'm going to take the other one, g of x, and plug it in where I had the x in this function. So this will be x squared. Okay, well, I can simplify that kinda. I don't really need the parentheses. So f composed of g of x is x squared plus 2. Any questions? All right. Now we also said that the direction that we do this also matters. So f composed of g isn't necessarily the same thing as g composed of f. So let's check and see what that comes out to be here. So g composed of f of x is going to be basically the same idea. We've got x squared here. We're going to open up our parentheses for that x and then add whatever else is left. So we'll plug in f of x for this parentheses here. So we've got x plus 2. And now we can go ahead and multiply that. And we should get something like g composed of f if x is equal to x squared plus 4x plus 4. So yeah, no, they are not the same thing. That's what you can expect to see most of the time when you're working with these functions and composing them. Most of the time you're going to see that they come out to be totally different things depending on which direction you plug them in. Sometimes though, like we saw on Friday, you can get functions that no matter which way you compose them, it comes out to be the same thing. Okay, now this is pretty useful, especially in finding inverse functions, which we'll talk about a little bit more towards the end of lecture today. But it is not the only way that we can put functions together. In fact, we can also use all of our operations from algebra in putting these functions together. For instance, I can do f plus g. Okay? So if I want to do f plus g, what it means is I'm literally going to take the f function and add the g function to it. Now I'm going to come up with some different functions here just to make it work a little better. So let's say that my new f is x plus 2. I'm not x plus 2, I'm sorry, x squared plus 2. And then my new g function is 3x squared minus 4. Could I have done it with those up there? Sure, but these are going to look more interesting. Okay, so f plus g of x works exactly like you think it might. We're going to take f, which is x squared plus 2. Whoops, running out of ink there. So again, x squared plus 2 for f. And then we're going to add g of x, which is 3x squared minus 4. Now, of course, it's better to use parentheses around these when you plug them in, but I know because we're just adding, I don't need those parentheses. Okay, well, now it's just a matter of simplifying, and all we can do here is combine like terms. So I've got x squared and 3x squared. If I combine those, I get 4x squared. Then I've got 2 and negative 4, so that's going to give me negative 2. And there we go. So f plus g of x gives us 4x squared minus 2. Now here's a question for you. We know that f composed of g and g composed of f, like we have up here, usually do not come out to be the same thing. So here's my question. We know f plus g is this. If I do g plus f, will I get a different function? What do you think? Probably what?
Probably not.
No, absolutely not, I won't. There's a very good reason for it. It's because we're adding. And addition has this property that we've learned about in the beginning of the semester called the commutative property. And that property says that if you're adding two things, it doesn't matter which way they go. If you add it one way or the other, it's going to get you the same sum. So we know that since we're adding and using that commutative property, that if we do f plus g, it will be the same thing as if we did g plus f. Very good. Any questions? Okay. Now, what about the opposite? What if instead I want to do f minus g? So do you think that the direction is going to matter on this one?
No.
No? All right, let's see. I really need to replace this pen. All right, so my f, again, is x squared plus 2. I'm going to put this one in parentheses because I know that I don't have this commutative property working for me. Okay? Then, of course, we're doing subtract, so I'm going to do minus g of f, which is, I'm sorry, g of x, which is 3x squared minus 4. Okay. So first things first, I need to distribute that negative into this set of parentheses here. Let's see, x squared minus 3x squared is going to be negative 2x squared. Okay, and then 2 minus negative 4, that's plus 4. So 2 plus 4 is 6. So I get that f minus g of x is negative 2x squared plus 6. Okay. So now let's see what happens if we do g minus f. Again, like I said, I don't have the commutative property working for me, so it's probably not going to come out to be the same thing. So we have g minus f of x will be, this time, 3x squared minus 4 minus x squared plus 2. Okay, so distribute that negative into here. We get negative x squared and negative 2. So 3x squared minus x squared is going to be 2x squared, positive 2x squared. And then negative 4 minus 2 is going to give me negative 6. So g minus f of x is positive 2x squared minus 6. Now if we look at these, they look very similar with one big difference. Their signs are flipped. So, are they the same? Can we just take this and say, all right, we know what the other one is? No. And it's because subtraction does not have a commutative property. So addition, we can just do it one way and it'll come out to be the same thing no matter which way we do it. Subtraction does not commute, so it's not going to work like that. You got to do both of them. I mean, if you need to do both of them. Okay. So how about not just add and subtract, but multiply and divide? Let's try that out. Let's try f times g of x. Now, does multiplication have a commutative property to it? Yes, it does. Multiplication does have a commutative property. So, we can say, without even having to work on this one, that no matter which way we do it, f times g or g times f, it's going to be the same thing. Okay? Let's see. I've got x squared plus 2 here. And then I'm going to multiply that by 3x squared minus 4. So let's see what that gives us. First of all, we've got x squared times 3x squared. That's going to give us 3x to the 4th. Then I've got x squared times negative 4. That's going to be negative 4x squared. 2 times 3x squared is 6x squared. And then 2 times negative 4 is negative 8. Simplify it a little bit, and we get 3x squared. Not 4, not squared, 4, squared, 3x to the 4th, plus 2x squared minus 8. Okay? Any questions? Now, again, what we said here is that because multiplication has a commutative property to it, then we don't need to do g of f. We know what it's going to be. It's going to be the same thing as this. How about division? Does division have a commutative property? No. So if we did division, then we'd have to do both of them to know what both of them would be. Now, division's a little bit hard to come up with examples for. I don't have one in front of me, but I'll give you an idea. Let's say that we have, we're separating this from these, so ignore the f and g up here. We're focusing on something new. Let's say that we have f divided by g. And when we do that, we of course get a fraction. The top part would be f, the bottom part would be g. So I'm going to say that we have factors up here, that we've maybe factored f and we factored g and we found their factored forms. This is x minus 1 times 3x plus 1. And then on the bottom we have maybe something like x minus 1 and 2x plus 3. So again, the top part is f, the bottom part is g. And what we've done is we've factored them. Well, as you can imagine, just like when we were working with rational expressions a couple weeks ago, anything that's common between top and bottom would be canceled. And so we take those out and we get just 3x plus 1 over 2x plus 3. Now again, it's non-commutative, so if we did g over f, it would come out to be almost the same thing, except we would have 2x plus 3 over 3x plus 1. Does that make sense?
Yeah, anytime you have anything over something else, things that are alike cancels out, and then you do the other side, like we did g over f, it'd be 2x plus 3 over
Good.
3x plus 1.
Yeah. Now, I'm not sure that Mr. Mrzinski or I will give you one to actually factor out and do. Typically, it's going to look something like this. So let's say that we have f of 3 is equal to, let's say, 4. And then g of 3 is equal to 2. Then what is f divided by g of 3? So we don't have f divided by g. In fact, we don't know what the actual function for f or g is. But what we do have is points. So when we plug in x for 3, we get 4 here. When we plug in a 3 over here for x, we get 2. Now, if we knew the functions here and divided them, we'd get a new function that would have some point at 3. What is that going to be? Well, it's going to be exactly what we see here. F divided by g, we're going to do 4 divided by 2. Because they're all at the same 3 point. So 4 divided by 2 is 2.
You said would y'all ever give us one that the points weren't the same, so like this one has 3, they'll always be the same no matter what?
Mm-hmm.
Okay.
That's what we're going to give you.
Okay.
And of course, you can imagine that that would work for any kind of operation that you're doing. If you're doing f plus g, it'd be the same thing. You do 4 plus 2, you get 6. Make sense?
Yeah.
Okay. So let's talk more about inverses. Again, like we said on Friday, an inverse function is a function which does the exact opposite of a parent function. So if I have the parent function f of x equals 2x minus 3, then there is some function out there that does the exact opposite of this. Something that if we were to compose this of its inverse function, everything would cancel except for that x. So let's find the inverse function of this. But first, let's also graph this one so that we know what its graph looks like. So I'll make up a grid.
Using the inverse function, everything cancels except for the 3.
Except for the x.
Oh, except for the x.
If you think about it, negative 3, it's doing something to x. 2 times is doing something to x. The inverse function would be doing the exact opposite of those things, and so it would cancel those. So the 2 would cancel. It'd be like divided by 2 or something. The 3 would also cancel, and so all we would have is just the base thing, which is x. Everything we're doing to x would have canceled each other. Okay, so let's go ahead and graph this. So we know how to graph these. First of all, we need our y-intercept to get a single point. So my y-intercept is negative 3. That means I'm going to go down 1, 2, 3, and I've got a point right there. Then we use the slope to find the other points. So this slope is positive 2, which as a fraction would be 2 over 1. That means that we're going to be going up 2 and over to the right 1. So I'll go ahead and do that. Up 1, 2 over the right 1. Up 1, 2 over the right 1. I'll do one more. Up 2 over the right 1. And so we can see a line emerging here. And if I go ahead and draw a line through these points, whoops, that's still fine. We have a function. We have a graph of a function. Now, being that, in order to get an inverse function, we need to do the opposite of all that kind of stuff. What does the graph of the inverse function look like in comparison to the parent function? Well, let's find out. So, again, like we did on Friday, we're going to find the inverse function. And the way we do that is, instead of writing f of x, we're going to use y. Because remember that f of x does represent y. Like we keep saying, an inverse does the exact opposite of what the parent function does. So in order to get that, what we're going to do is we're going to flip the positions of x and y. So x is going to go over here, and y will be over here. With me so far?
Yeah.
All right. So now our goal will be to get y by itself, to solve for it, in other words. So the first thing that I can do is add 3 to both sides. That gives me x plus 3 equals 2 times y. And then divide by 2 on both sides to get y equals x plus 3 over 2. Okay, now it's a little bit hard to see, but this is still a linear function. I can rework it a little bit, make this f to the negative 1 of x is equal to, let's see, x divided by 2, that's like 1/2 x. And then plus 3 over 2. So it is still a linear function. It's y equals mx plus b. So we should get another line. Well, let's see. So our y-intercept is positive 3 over 2. That means 1 and 1/2. So I'm going to go up 1 and 1/2 on my y, and I've got a point like right there. Now my slope says 1 over 2, so that means I'm going to go up 1 and over to the right 2. So up 1 over the right 1, 2. Up 1 over the right 1, 2. Up 1 over the right 1, 2. It's like that. All right. So we have an inverse function, and we have its graph. What does this actually mean, though? I mean, right now it's just lines on a paper. Okay. So an inverse function. For one thing, you can see that there is a point where they cross, where they're going to be the same. And funny enough, let's look at that point. What is it? Well, on the x it's 1, 2, 3, and on the y it's 1, 2, 3. And that isn't a coincidence. The fact that they both share the point 3, 3 comes down to what we did to get our inverse function. We flipped x and y, didn't we? Well, what happens if you flip the point 3, 3? If you flip the positions of x and y? It's still 3, 3. Well, what about the rest of our points then, from our parent function? So like this one here, this is negative 1, 2, 3. This is 0, negative 3. So what happens if we flip that, if we make it negative 3, 0? Well, that'd be negative 1, 2, 3, 0. There's a point on that line. How about this one? This one is 1, negative 1. So then we flip that, be negative 1, 1, negative 1, 1. Got another point on our line. In fact, that's exactly what this is doing. Every single point on this line, if we were to flip their x and y parts, we would get every single point on this line. That's all an inverse function does. It flips your x and y coordinates. Any questions? Okay, let's try one more of these. But before we do that, I want to go back to how we define a function. A function is a machine. A function is just something that has operations in it. We can plug in an x and get something out for y, right? Now, let's think. We plug something else, or we plug something in for x, and we get something else out for y. Can we plug something in for x and get two different things for y? Two different values for y? Yeah, absolutely, right? In fact, we know what that looks like. It's a parabola. Let me get another one out. I'm going to draw the function f of x equals x squared. Okay, so f of x equals x squared. I know that's a quadratic, and I would need to find the vertex, the x-intercepts, and the y-intercepts. But in that one, in f of x equals x squared, they're all right here. Just that point. So now what I need to do is be like, okay, well, if I plug in a 1 for x, what do I get for y? 1. If I plug in a negative 1 for x, what do I get for y? Well, I still get 1, don't I? Okay, if I plug in a 2 for x, what do I get for y? X squared. 4. Yeah, so 2 is 1, 2, 3, 4. If I plug in negative x, that is 2. So negative 2 for x. That's positive 4 still. So the same y coordinate can get different x coordinates. As we can see here, if we have x equals 2, we get y equals 4. If we have x equals negative 2, y is still 4. But that's fine. Okay? In fact, we could keep going with this. Let's see. So 3 would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And no matter how many points we get on here, y will always line up with 2 different x values. Every value for y will line up with 2 different x values. So now the question is, can we make the opposite true? If every single y, so for instance y equals 4, has 2 different x values, can x have 2 different y values? So if I have this right here, this x value, 1, can I get 2 different y values for that 1? Well, if x is 1, 1 squared is 1, right? So it only gives me one of them. Okay, what about the inverse function? Well, rather than going through this and doing square roots, because I know I'd have to deal with square roots, all I'm going to do is flip x and y. So like 0, 0, if I flip that, that's still 0, 0, right? So it's actually shared for the inverse function, and I'm going to start graphing that. So inverse function shares that. How about 1, 1? Inverse function is going to share that one too. It's also 1, 1. The difference, though, is this one. This is negative 1, positive 1. Flip that, I get positive 1, negative 1. Okay. How about this one? This is 2, 4. Flip that, I would get 4, 2. So 1, 2, 3, 4, 1, 2 is right there. And then this one is negative 2, 4. So I flip that, I get 4, then negative 1, 2. Okay, so now I've got all of the inverse points plotted, and Well, it looks like the same graph just turned 90 degrees. But what does this mean? Well, it means that an x value, like 1, can make two y values, like -1 and +1. So, in this original, every x value had its independent y value. Y's could repeat, x's could not. Okay? In this one, we have x's getting two different y values. That means that they're repeating. Now the point of this comes down to how we define functions. Functions, we are plugging in something for x. So we plug in like 3 and we get a particular number out for x. And for a function to be a function, the definition says that x always has to get a unique value. X cannot get more than one value. Its value must be unique. So if I plug in 1 for x, I better get just one thing. Another way of testing this is called the vertical line test, which means that we pass a vertical line, you can imagine the edge of this ruler as a vertical line, through our graph. And as long as it only passes in one point on this line, then it's a function. So like this one right here, I can pass it through, and at only one point does that graph cross through my vertical line. As soon as I get to that inverse function, it starts crossing in 2 points, meaning that each x value does not have a unique y value. It's sharing them. So what we would say about this is that the inverse is not a function. Or we could even say that f of x equals x squared does not have an inverse function. Now, sometimes you see people getting away with it by saying, well, we're just going to ignore these points at the bottom and just have this part. Okay, that's fine. This is a function. However, just this arm would not count as the inverse for this. So this is a function, but they're not inverse of each other. Does that make sense? Okay. So f of x equals x squared does not have an inverse. So then let me ask you this. Does any quadratic function have an inverse?
Yes.
Do what?
I said yes, but I'm changing my mind to no.
Okay. So we got to think about it. Any quadratic function is going to give us a parabola like that. It doesn't matter what it is. Sometimes it'll be shifted up here. Sometimes it'll be flipped down to the bottom. Sometimes, whatever. But it's always going to have this shape. And no matter its orientation, it's always either going to be pointing up or pointing down. And if we flip that 90 degrees, well, hey, we've got something that violates the vertical line test. So quadratics do not have inverses. They give us something, but it is not an inverse function. It'll have an inverse, but it won't be a function. All right, any questions? All right, then I think that'll do it for today. So Wednesday, we're going to be having a quiz over functions. So no meeting in class Wednesday. Just get that quiz done, and please get the quiz back to me before Friday.
Okay.
But that's it, so I'll see you on Friday.